All right, it is now time to talk about another algorithm, and we're going to be talking about word2vec. And this algorithm was actually created by a team of researchers over at Google. So it must be good, right? So we'll get right into it. And what I'm going to do first is I'm going to attach an image so you can understand word2vec in more simple terms. You don't have to do this part, just pay attention on the screen. If you prefer though, you will of course need this image. So if I was you, I would just follow along here. So I'm going to type in from ipython.display, import image, and then the next line image, and then in parentheses with double quotation marks around word2vec.png. So there is the image that will help you understand things as I go through it here. But the idea behind word2vec is pretty simple. We're making an assumption that the meaning of a word can be inferred by the company it keeps. So if you have two words that have very similar neighbors, meaning the context in which it's used is about the same, then these words are probably quite similar in meaning, or at least related. For example, the words king, queen, and prince are usually used in a similar context. So we can say that the meaning of a word can be inferred by the company it keeps. And what word2vec does is it takes raw text as input and learns a word by predicting its surrounding context or predicting a word given its surrounding context. Now, using this underlying assumption, we can use word2vec to surface similar concepts, find unrelated concepts, compute similarity between two words, and much more. For example, if we want to filter our mailbox to get just the job-related emails, we can train a word2vec model with job-related emails. And then when we get a new email, we can predict that if it's a job-related email or not by looking at the similarities between words. Or if we want to build a recommendation system, we can treat these shopping items bought together as a word in a sentence and then recommend a new item to consumers by looking at what he or she actually bought. So, word embeddings use numbers to represent words. Each of those numbers is in a dimension, and each locates a word in, say, a 300-dimensional space. Once word embeddings have been trained, you can use them to derive similarities between words as well as other relations. The typical example for word embeddings is that they allow you to perform math like this. King minus queen equals man minus woman, because the difference between the word embeddings is similar, and therefore king minus queen plus woman equals man. So by manipulating the equation, you can actually derive relationships that you didn't know existed. Basically, all words in the corpus we deal with can be represented by the word vector in a desired number of dimensions, and then we can use this vector representation to find relationships between the words. Using large amounts of unannotated plain text, word2vec learns relationships between words automatically. The output are vectors, one vector per word, with remarkable linear relationships that allow us to make some inferences. So here's an example, and this is a 25-dimensional word vector of the word hello, which is basically an array of numbers which represent semantic or syntactic information of words in a way that computers can understand. So we're going to get going and we're going to see how to build our own word2vec model using the GenSim library, which of course we introduced earlier in the course. So let's import GenSim to begin with. The next thing is really finding a really good data set. The secret to getting word2vec really working for you is to have lots and lots of text data in the relevant domain. So we'll use open source BBC News data sets corresponding to stories in 5 topical areas from 2004-2005. And there are 5 class labels: business, entertainment, politics, sport, and tech. And we will make this data set available for you guys so you can download it. So we're going to start with sports related news. First, we'll get the list of text files under BBC_sport folder so that we can pass this on to the word2vec model. We can use the glob library for that. So we're going to import glob. The next line, file_names equals glob.glob. And then in parentheses with double quotation marks, BBC_sport, the /, the asterisk dot txt, and of course close that up with the parentheses. And this is what we get, our output. And you will get a long output here. So just have a quick look at that. We're going to read a single file to just see how this looks. So with opening parentheses, apostrophe, BBC_sport, /394.txt, closing apostrophe, comma, and then double quotation marks around R, comma, encoding equals double quotation marks, UTF/8, closing double quotation marks, closing parentheses, as F colon, and the next line, print, opening parentheses, F dot read, opening parentheses, closing parentheses, and then closing parentheses. So this is what you will get. Now we'll read all of the TXT files into one single list. So a list, we're going to create a list of texts. Sport_text_list equals, and then opening and closing square brackets. Next line, for file in file_names, colon. The next line, try, colon, and we'll use try catch block here to prevent the code from crashing if it cannot read any of the TXT files. And then next line, with opening parentheses, file, comma, double quotation marks are on R, comma, encoding equals, opening double quotation marks, UTF/8, double quotation marks to close out, closing parentheses, as F colon. Next line, sport_text_list dot append, opening parentheses, F dot read, opening parentheses, closing parentheses, closing parentheses. Next line, except colon, and the next line, pass. So now what we're going to do is we're going to apply some text pre-processing to clean the text. Apart from what we did before, we'll use a pre-processing tool from the gensim library. This does some basic pre-processing such as tokenization, lowercasing, and so forth, and returns back a list of tokens or words except stop word removal. Documentation of this pre-processing method can be found on the official gensim documentation site, and we will give you a link to that. So let's type in import gensim, and then clean_texts equals, opening and closing square brackets. Next line, for text in sport underscore text underscore list colon. And the next line, clean underscore texts dot append, opening parentheses, gensim dot utils dot simple underscore preprocess, opening parentheses, text, closing parentheses, and another closing parentheses. So let's take a look at the first preprocessed text from our corpus. To do that, we'll do clean underscore texts, and then in the square brackets, we'll put 3. And there's the output for that. It is now time to train the word2vec model, and training the model is fairly straightforward. You just instantiate word2vec and pass the reviews that we read in the previous step. So we're essentially passing on a list of lists where each list within the main list contains a set of tokens from a user review. Word2vec uses all these tokens to internally create a vocabulary. And by vocabulary, I just mean a set of unique words. I'm going to copy and paste this part of the code, as the video is getting a bit big. All we're doing is we're building a vocabulary and training the model. And all the parameters, if you want to know exactly what they stand for and mean, take a look at the gensim documentation, and all that stuff in the parentheses will be very, very clear. So we can take a look as well how our vector looks like. And so I'm just going to copy and paste this part of the code as well. And this output that you see is how it's a representation, a vector representation of our whole vocabulary. So that is what this is. Now we can also see the vector representation of just a single word. So in this case, I'm going to type in word equals and then in double quotation marks Celtic, and then next line model, opening square brackets, word, closing square brackets, dot to list, opening and closing parentheses. And now this is a vector representation of just a single word, and that word being, of course, Celtic. So there's the output for that. Now, after building the vocabulary, we just need to call train to start training the word2vec model. Behind the scenes, what's happening here is that we're training a neural network with a single hidden layer where we train the model to predict the current word based on the context using the default neural architecture. However, we're not going to use the neural network after training. Instead, the goal is to learn the weights of the hidden layer. These weights are essentially the word vectors that we're trying to learn. The resulting learned vector is also known as the embeddings. You can think of these embeddings as some features that describe the target word. For example, the word king may be described by the gender, age, the type of people the king associates with, etc. Let's see similarity on some sport types. This first example shows a simple lookup of words similar to the word match. All we need to do here is to call the most underscore similar function and provide the word match as the positive example. This returns the top 10 similar words. So let's do that. We'll type in word equals and then in double quotation marks match, and then next line model dot wv dot most underscore similar, and then in parentheses positive equals word, closing parentheses, and this is what we get. Let's try the same with an adjective. We'll try it with good. So word equals in double quotation marks good, and then model dot wv dot most underscore similar, and then in parentheses positive equals word, and then we get a bunch of output for that as well. Let's now try it with a sport club name like Celtic. So word equals, in double quotation mark, Celtic, and then again, model.wv.most underscore similar, and then in parentheses, positive equals word. And then you get your similarity matches there as well. So overall, the results actually make sense. All of the related words tend to be used in similar contexts. Now you could even use word2vec to compute similarity between two words in the vocabulary by invoking the similarity function and passing in the relevant words. So for example, we can type in model.wv.similarity and then opening parentheses, W1 equals, in double quotation marks, Celtic, comma, W2 equals Nottingham, in double quotation marks, and then closing parentheses. And it shows us that the similarity is 0.9. It goes up to 1. So apparently these are very similar words. So let's try another one. Model.wv.similarity. And we'll try the first word good, and the second word we'll put in as bad. And we'll see what we get with that. So the output for that, 0.67. So not as a good match as Celtic and Nottingham are. Let's do another one with good and great. So let's try good and great. And as you see, we get a 0.76 here. And we'll try one more. How about well and bad? And since these are kind of opposite, you would expect that it's not going to be that similar. And in fact, you get 0.52, 2967, and so forth. So under the hood, the above 4 snippets compute the cosine similarity between the two specific words using word vectors, embeddings of each. From the scores above, it makes sense that Celtic is highly similar to Nottingham, but good is dissimilar to bad, of course, because they're opposites. If you do a similarity between two identical words, the score will be 1.0, as the range of the cosine similarity score will always be between 0 and 1. So for example, if we do it with the first word being good and the second word being good as well, look at the output that we get. So just a perfect one, which makes sense, right? Now, what if we did it with kind of similar words, but not quite? Kids being the first word and boys being the second word. And notice that we get a 0.8, so very, very similar. How about if we do, on the other hand, and this will be the last one we'll do for this video, how about if we do the first word kids and the second word men? Well, this shouldn't be really similar. Kids and men is not very similar. And look at the output, 0.06, so not very similar. Hope you've enjoyed this video.